Welcome to the deep dive. Today, we're jumping straight into a concept that feels, well, almost like science fiction made real-time crystals.
Right.
If you're looking to quickly get your head around some truly mind-bending science, without wading through dense academic papers, you're definitely in the right place.
And you might be thinking, can something actually move forever without using any energy? I mean, it sounds like a fundamental impossibility, doesn't it?
It really does. It seems to fly right in the face of basic physics.
Especially the second law of thermodynamics, yeah.
Yeah.
Which essentially tells us perpetual motion in, a closed system is pretty much a no-go zone.
Exactly. And that's where this idea of time crystals crashes the party, so to speak.
Uh-huh.
Back in 2012, Nobel laureate Frank Wilczek proposed this incredible idea, a new state of matter.
A completely new state.
Yeah, one that exhibits repetitive motion not in space, like, say, a spinning top.
Or regular crystal lattice.
Right, but in time itself. And crucially, without needing any energy input to keep going.
That's the kicker. No energy needed. He called it a time crystal.
That's a great name.
It is. And maybe think about ordinary crystals for a second, just to contrast. Like a diamond or maybe a snowflake.
Okay.
They have a structure, right? A pattern of atoms that repeats perfectly in 3 dimensions, in space.
Right, a spatial pattern.
Precisely. What Wilczek suggested is kind of similar, but instead of that spatial repetition, you have a system where certain properties oscillate or repeat at regular intervals in time.
Even when the system is like completely at rest, lowest energy state.
Exactly. Even when it's in its ground state, its lowest possible energy state. That's what makes it so weird.
Okay, let's unpack this a bit then. So the core insight here, the thing to really grab onto, is it's not a repeating pattern in space, it's a repeating pattern in time.
You got it.
Wilczek used an analogy, didn't he? Something
Yeah.
about a clock.
Yeah, imagine a clock that just keeps ticking perfectly, regularly, and you never, ever need to wind it.
Never needs winding. Okay, that's the kind of perpetual motion in time we're talking about.
That's the essence of the initial theoretical proposal.
Just theoretical then.
Well, that's what's truly remarkable. This theoretical idea, it actually made the leap
From theory to...
to experimental observation.
Yeah,
Yeah, in 2017. 2 separate research teams working independently.
2 groups at the same time.
Pretty much. They both managed to create and observe time crystals in their labs. It was a huge confirmation.
Wow. Okay, but these weren't like everyday objects you could just pick up and look at. Were
Oh, definitely not. No, this happened within very, very precisely controlled quantum systems.
quantum systems. So we're talking tiny scale.
Extremely tiny. The experiments involved manipulating qubits.
Qubits.
Yeah,
The basic building blocks for quantum computers.
that's them. They used different physical setups, too. One group used trapped ions, basically charged atoms held in place,
Okay.
and the other used the spins of atoms within a diamond lattice. So, different approaches, but the same result.
Right. And how did they coax these systems into behaving like time crystals? They didn't just spontaneously start ticking, did they?
No, it required some careful prodding. They applied very carefully timed sequences of pulses, like laser pulses or microwave pulses, to these qubits.
Acting as a kind of driving force, like pushing a swing.
Sort of, yeah, a periodic push. What they then observed was the system starting to oscillate, moving back and forth in a predictable way over time.
Okay, predictable oscillation.
But here's the really key takeaway, the defining feature. The period of this oscillation, how long it took to complete one cycle.
Yeah.
It was exactly double the period of the pulses they were applying.
Wait, double. So they're pushing it, say, every 2 seconds.
Yeah.
And the system responds every 4 seconds.
Precisely. Consistently, stably, every 4 seconds.
So they were nudging the system at one rhythm, but the system was responding with its own slower rhythm.
Its own distinct rhythm, exactly.
Yeah.
And this response was stable and ongoing.
The crucial insight, then, is that the system isn't just, like, echoing the input pulse.
Not at all.
It's establishing its own independent rhythm in time. Is that it?
That is absolutely it. This behavior is the defining characteristic of what scientists call discrete time translation symmetry breaking.
Okay, discrete time translation symmetry breaking.
That's a mouthful.
It is, but the concept is key. Normally, if you drive a system with a periodic force, you expect it to respond with the same period, right? Same rhythm in, same rhythm out.
Makes sense.
But the time crystal breaks this symmetry. It picks its own period, a different, longer one.
So it sort of ignores the driving beat and marches to its own drum?
A slower drum, but a very precise one. Think of it like a perfectly synchronized dance where you're playing the music,
Okay.
And you expect each step to follow your beat. But instead, the dancers establish their own slower but equally precise sequence of movements. It's locked in, but at a different frequency.
Let's go back to that swing analogy, pushing it every 2 seconds.
Right. But instead of swinging back and forth every 2 seconds, it just naturally falls into a 4-second cycle.
And stays there.
All on its own, seemingly. Forever. That forever part is still kind of hard to grasp.
It is. In the context of these experiments, it means stable over the observation time, resisting perturbations, and this stable, self-sustaining oscillation at a different rhythm. It's not just some quirky lab observation, right?
And no, it feels more fundamental.
It really does. This kind of departure from expected behavior at the quantum level, it makes you wonder, where does that lead us?
Yeah, in terms of real-world implications.
Exactly. What's fascinating is how this fundamental weirdness in quantum systems could actually be leveraged.
Okay, so we have these bizarre entities, these time crystals, that seem to bend our classical understanding of things. But why should someone someone looking to quickly grasp important science, why should they care beyond just the strangeness?
That's a fair question.
What are the potential real-world impacts people are talking about?
Well, one of the most promising areas, and maybe the most talked about, is within quantum computing.
Ah.
As you know, qubits are incredibly delicate. They're super prone to errors from environmental noise. It's a huge headache.
Decoherence, right. Losing their quantum state.
Exactly. The idea is that the stable, repetitive time behavior of time crystals could potentially be harnessed, maybe used to create more robust qubits.
More robust how?
Well, their inherent stability, that locked-in rhythm, might protect the quantum information they hold, leading to significantly lower error rates in quantum computations.
Wow. Imagine the impact if the very building blocks of these future computers were inherently more stable.
It would be massive.
Yeah.
Error correction is, like you said, a major roadblock right now in building practical, large-scale quantum computers.
So a time crystal-based qubit, that could be a real game changer for reliability.
It potentially could, yes.
Yeah. What other potential applications are being kicked around?
Another really intriguing possibility is in energy-efficient memory storage.
Memory, like computer memory.
Yeah. Imagine devices that could hold information pretty much indefinitely, but with almost zero power drain.
Zero power drain. That sounds, again, impossible.
Well, ultra-low power, perhaps? That's the tantalizing potential here. Time crystals, with their inherent periodicity, their self-sustaining oscillation, maybe they could form the basis for such memory.
So we're not just talking about faster computers, potentially, but also fundamentally more efficient ways to store and access information.
That's the hope.
That could impact everything from, I don't know, your phone to massive data centers.
Indeed. But the significance of time crystals, it really extends beyond just these potential tech applications, important as they are.
Okay.
If we try to connect this to the bigger picture, their very existence challenges some of our most fundamental assumptions about physics.
How so? You mentioned the second law of thermodynamics earlier. That seems like a big one to challenge.
It is. The second law basically states that entropy, disorder in a closed system tends to increase over time. Things run down.
Right. Order decays into chaos.
Generally, yes. But a time crystal, exhibiting this persistent order and motion without energy input, seems to exist right at the edge of this law, or at least forces us to look at it very closely in the quantum context.
So it compels us to reconsider that relationship between energy, order, and time.
Especially when we delve into the quantum realm, yes, it complicates the picture in fascinating ways.
And what about this idea of time symmetry you mentioned? What fundamental assumptions are being challenged there?
Right. So at a really fundamental level, many of the bedrock laws of physics are what we call time symmetric.
Meaning they work the same forwards or backwards in time.
Exactly. Like gravity or electromagnetism. The equations don't care which way time flows, but the spontaneous breaking of time translation symmetry in time crystals.
That predictable repeating, but at its own pace.
Yes. That suggests that time itself might not be as, let's say, uniform or featureless as we often assume, at least not within certain quantum systems. It can have structure.
Whoa. Okay, this raises a pretty profound question then. Could this have implications for how we understand the universe at its most fundamental levels?
Potentially.
Maybe even touching on the big mysteries like quantum gravity or cosmology?
It's certainly a line of inquiry that researchers are actively pursuing now. It's very early days, of course.
Sure.
But the unique behavior of time crystals, the symmetry breaking in time, it might offer new perspectives on concepts like the arrow of time, why time seems to flow only one way for us.
Or even the fabric of space-time itself.
Perhaps. And there's been recent work, too, like a study in 2022 by me and colleagues.
What did they do?
They demonstrated time crystal phases, but in a programmable quantum processor, like Google's Sycamore processor.
Ah, so moving towards more complex, controllable systems.
Exactly. Which is exciting because it shows the potential for creating and manipulating these states in more scalable systems. That brings us closer to maybe understanding their broader implications and possibly harnessing them.
You said something earlier. This isn't just quantum bling. It could be the architecture for future quantum machines. That really reframes it, doesn't it?
I think so. It emphasizes that it's not just a strange curiosity, a weird footnote in physics. It could be a foundational element.
A building block for the technologies of tomorrow.
Potentially, yes. Now, this might be a good point to venture into some of the more, let's say, philosophical and even cosmic questions that time crystals bring up.
Okay, let's get speculative. This is where it gets really mind-bending.
It does, because the implications ripple outwards.
I'm ready. Let's tweak reality a bit. What are the big questions that keep physicists up at night?
Well, one of the immediate questions that arises is sort of fundamental. If we can create a system in the lab that breaks time translation symmetry,
Yeah.
could time itself be just another type of symmetry, like spatial symmetry, that can be broken in other contexts naturally?
Meaning, could there be natural time crystal-like structures just existing out there in the universe?
Exactly. Not just within our carefully controlled, very specific lab experiments.
Wow, that's a wild thought. Could there be naturally occurring phenomena that just tick perpetually with their own rhythm?
It's a completely open question right now. We have no evidence for it, really.
Gotcha.
But some researchers have speculated
Speculated about what?
about potential links between time crystals and, say, the persistent oscillations observed in certain astrophysical objects. Weird radio bursts, maybe?
Pulsars?
Could those be manifestations of some underlying time crystal behavior on a cosmic scale?
Again, pure speculation at this point. We really don't have definitive answers or even strong candidates. But it's a fascinating area to think about, to investigate.
And what about even larger scales? You mentioned cosmology earlier.
Right.
Could time crystals offer any insights into the fundamental nature of the universe itself? Maybe its potential cyclic nature or, theoretical ideas like time loops?
These are definitely highly speculative concepts. Way out there.
Fair enough.
But the very discovery of time crystals does encourage us to think in fundamentally different ways about time itself. If time isn't always the smooth, uniform river, but can have structure, can break symmetry.
Then it potentially opens up new avenues for revisiting
Yeah.
some of these more unconventional cosmological theories. It just changes the way we frame the questions.
Of course, I imagine there's a healthy dose of skepticism among physicists, too.
Oh, absolutely.
Especially regarding whether we'll see practical applications of time crystals outside of these very specific, very controlled laboratory conditions.
Yes, that's a major point of discussion. Some argue that the precise conditions required, the intense cooling, the specific pulse sequences, the isolation from noise,
They're just too artificial.
too artificial, maybe too delicate to be relevant in most real-world scenarios, or even in slightly less controlled quantum computers. There's an ongoing scientific debate about the robustness and scalability of these systems.
What are the key hurdles there? Is it just maintaining the quantum state?
That's a big part of it, maintaining that delicate quantum coherence. But there are also questions about the definition itself, about whether these driven systems truly count as a new phase of matter, in the same way a solid or liquid does. The field is still evolving.
Still finding its feet, in a way.
You could say that. But then, on the flip side of the skepticism, you also raised that intriguing possibility earlier.
Using them in deep space probes.
Yeah, that sounds like something straight out of Arthur C. Clarke.
It really does. How might they be applied there? What's the thinking?
Well, the underlying idea is that inherent stability we talked about, and the near-zero energy requirements, theoretically.
Right.
Could that stability be harnessed to create incredibly accurate, incredibly long-lasting clocks?
Our navigation across vast interstellar distances.
Potentially. Or maybe even to power certain scientific instruments with minimal energy expenditure over missions that last decades or centuries.
Wow, it's a very long-term vision, isn't it?
Extremely long-term, but the potential is certainly compelling, very imaginative.
So, from maybe stabilizing the quantum computers of the future to perhaps revolutionizing how we explore deep space someday, The implications, even if they're largely theoretical at this stage, are quite
They
staggering.
really are.
It really makes you ponder. Could time crystals in some, distant future contribute to building machines that operate on timescales approaching the lifespan of the universe itself?
That's exactly the kind of profound question that this discovery compels us to consider, isn't it? It challenges our foundational understanding of energy, motion, the very fabric of time.
It's something that, as you said, still gives physicists pause.
Definitely. This persistent motion at the quantum level, without apparent energy cost in the oscillation itself, it feels so deeply counterintuitive to our everyday classical experience of the world.
Well, this has certainly been a deeply mind-bending exploration today.
It's a fascinating topic.
Time crystals a concept that really challenges our fundamental understanding of time and energy, and yet it's another powerful reminder, isn't it,
Of what?
of the universe's seemingly endless capacity for surprise, for things we didn't even imagine were possible.
Well said.
Hmm.
And it really encourages us, I think, to keep questioning the nature of time itself and the fundamental symmetries, or lack thereof, that govern our universe.
Absolutely. So, as you go about your day, maybe take a moment to contemplate the nature of time, of symmetry. It might just resonate in your thoughts with a new, unexpected rhythm.
Nice.
Until our next deep dive, keep that curiosity alive.